We're going to have a look in this session around the development of transformation parameters, plate motion models, and deformation models. And I don't get into the specifics of how you implement this in the software or which grid file format, but this is more around the theory of how you develop them and what kind of data that you need to develop these models rather than the outputs. So a coordinate transformation refers to the change of the coordinates of a point, which are defined in one reference frame, to defining it in a different reference frame. And they are all based on Earth-centered coordinates. So the X, Y, Z from the center of the Earth, for example, in ITRF 1996, through to X, Y, Z coordinates in another reference frame like ITRF 2020. So a common type of geodetic transformation is a 7-parameter transformation. And as we mentioned yesterday, that includes these 7 components: the 3 translations, so the shift in the origin of the system, the 3 rotations, the angles around which the 3 axes rotate, and then the scale factor, which is the resizing of your reference frame due to the different scales of the coordinate axes. So to develop a 7-parameter transformation between the 2 systems, between the 2 reference frames, I should say, you need to know the Earth-centered Cartesian coordinates, X, Y, Z, in both frames at a number of different points. And when that 7-parameter transformation, when it's insufficient to achieve the accuracy required, you may need to do a 1, a 2, or a 3D deformation model as well. So that's that second step that I mentioned yesterday. You might try and apply a standard 7-parameter transformation, and that moves everything together. But remember, we looked at those residuals that were coming off from Europe, and we say that we minimize the residuals, but it didn't get rid of them all. So if you needed something more high accuracy, you've got to develop these deformation models in between. Jump over that. So this is what it looks like when you're trying to develop them. On the left-hand side is what you've got maybe your new coordinates in that might be in ITRF 2020, and then the original coordinates you can see down the other end of the equation in that might be in ITRF 1994 or something like that, whatever the old one is. You can then, in the middle are the transformation parameters you're solving for. So essentially you're doing an inverse equation of some of these to try and solve for the parameters in the middle, those translation, rotation, and scale parameters. And just for those of you who think with pictures, which is what I do, this is where it fits within our big reference frame, reference system diagram that I presented yesterday. Again, for those of you who think in pictures, they might be the markers in your old datum in red, and then you've got your new datum in blue. And at those points where you've got information in the red and the blue, you need the XYZ in the old datum and the new datum. You can use those common points to develop the transformation parameters. So for those of you who are thinking about the development of a new datum and you haven't done it yet, consider the importance of observing the old marks that have been used to make sure that you have coordinates in the new reference frame that you want. Let's say it's ITRF 2020, go and collect them on the old reference marks of the old static datum, because you're going to need those to perform that transformation, and that's going to be critical for your users to bring their old data set into the new reference frame. If your data is stored in latitudes, longitudes, and ellipsoidal heights, that's not a problem. You can do a conversion of the coordinates from lat, long, and height into Earth-centered Cartesian in X, Y, and Z, and all the transformations are done at that X, Y, Z level, and then you can do a coordinate conversion again at the bottom to take your X, Y, Zs and convert them to lat, long, height. So this is just a reminder, you've got to have your data in X, Y, and Z before you perform the transformation process. You can't use lat, longs, and heights. You then have this example where you might do your transformation, you find you've got residuals left over, and you've got to develop some sort of deformation model. And this is the case, this has been the case in Australia. We've had to do that. Not everyone needs that deformation component, but some people have wanted to use it. It's more prevalent in places like New Zealand, and we'll give you an example of how they've done it in New Zealand. But before we do that, let's have a look at an even simpler one, a 1D deformation model. This is the case for the Fennoscandia regions up around Sweden, Norway, Finland. And what we're seeing here is post-glacial land uplift. So as the ice has come off that region over a number of years, and it's happened, most of it happened a while ago, you get this, it's called a viscoelastic response. And the earth, the land is slowly rising over time. As that pressure came off, you get this slow rise of the land. And that's happening at sort of the 7 millimeters per year level. So they need to account for that land uplift in their modeling. And in their case, it's to do with the understanding their height datum. It still has an impact horizontally, but the biggest impact is vertically that they need to be aware of. We then have the example I've got here with Australia. This is showing that the Australian plate is, as it's the fastest moving continental plate, it's 7 centimeters per year. The GNSS provides coordinates in the ITRF position, which is the plate now. And if we didn't account for that plate motion, and going back to the old data sets in Australia of GDA 94, you'd see a 1.8 meter mismatch between the GNSS position and the spatial data sets that were recorded in GDA 94. And so we did some studies before working out whether or not we needed just the 7 parameter transformation or whether we also needed a deformation model. And in Australia, it's relatively free from large scale horizontal deformation from things like great earthquakes. Paul Tregoning from ANU did a study and was found that the uncertainty, the errors or the horizontal deformation is relatively low compared to the plate motion that you see. And it can be largely modeled through this clockwise rotation of the plate of about 7 centimeters per year. So we developed, we translated this 7 parameters into 14. And so that's giving you velocities. So you're applying a plate motion model and allows you to move the Australian plate backwards and forwards through time, depending on what timestamp that you want to record, whether it's the reference epoch at GDA 2020, or if you collected data today and you want to move it back to GDA 2020, you can just essentially rotate the Australian plate backwards and forwards through time using a plate motion model. Now, there's global models to do this, like I point out at the bottom, the ITRF develops these plate motion models for you, but only 17 points were used in the development of that ITRF model. So instead, we adopted to use our friend APREF. We used all the points from APREF that are on the Australian plate, and we used that to develop the plate motion model. Now, largely speaking, they give you almost the same result, but you get a more high resolution result and a more accurate result from using more data that was provided through APREF. So this is another example of where that regional work can really benefit you as a country. So here's an example of how it looks. If you think about the old static datum, we had GDA 94. That was based on ITRF 1992 with a reference epoch of 1994.0. And then if you look at the 7 centimeters through time, if you re-recorded that ITRF 1992 at 1995, you get 7 centimeters of movement in that northeast direction. Since that time, there were updates of ITRF. There was 1996, 97, 2000, 2005, 2008, 2014, and each improved realization of ITRF over time had an improved definition or realization of the shape of the Earth, which is great. And what we noticed was the difference between ITRF 2014 and ITRF 1992 was that there was 9 centimeters different in height. So that was quite a significant difference that needed to be taken into account. And it shows how these realizations of ITRF actually improve over time, because we had more SLR data, more VLBI data, more GNSS data. So we came up with a better defined definition of the Earth. All right, so we then applied try and apply a 7-parameter transformation. We want to go back from ITRF 2014 at 2020, apply a 7-parameter transformation to go back to ITRF 1992 at 1994, and they didn't match. How come? Well, there's a few reasons. The first was that there was changes in the reference frame between ITRF 1992 and today. There's local distortions. I said most of the Australian plate moves together, but it doesn't mean there's not local distortions in some places. But the biggest reason was the way in which GDA 94 was actually computed. And it was computed using this method of, we were talking about weighting our data yesterday with our national adjustment. What happened was, with the computational requirements you needed at the time to develop a datum, if you look at the top layer there, that's the ITRF points that we had drawn on the Butcher's paper yesterday. Effectively, they were held fixed in the national adjustment. So they had no wiggle room, no uncertainty. And then we used that to compute the Australian fiducial network points, which was, at the time, it was 8 or 9 points in Australia. And then we held that fixed and we propagated that down to the Australian national network that was 70 points, 78 points. And then we held that fixed. So you could see we're not propagating the uncertainty as we went down. We just held every adjustment above it fixed, which is not propagating the uncertainty down through the adjustment. The same way I showed you yesterday of how we could have different size circles and different weightings applied as we brought it all into one national adjustment. These were done as separate adjustments, holding the subsequent level, holding the level above fixed. So it wasn't quite rigorous, but it was fit for purpose at the time. And as a result, if you look at the differences between, once you take that 7 parameters and apply it, you look at the leftovers. These are some of the residuals that you see, particularly in the New South Wales region. This great piece of work was done by Joel and Tony out of New South Wales, and they presented this. And what it showed was, over time, they didn't go through and update the coordinate set in New South Wales to say, well, the coordinate isn't actually here, but it's over here. They kept it fixed at how it was defined back in GDA 1994. So when they took the 7 parameters and applied it and then looked at what was left over, you start to see these residuals. And for some people, particularly surveyors, this was important, because if they were to try and use the new datum and they just did a 7-parameter transformation to take the old coordinate set and move it on to the new one, they were going to get these residuals. They were going to have problems, and you don't want that, because that's going to affect property boundary rights. So what we did was we developed a deformation grid. And you can see here what we're looking at. It's pretty ugly, of course, but you can see that it's not consistent. In Queensland, they had a different example. So what Queensland did, they were continually updating their coordinate set. So as they had a refined understanding of the coordinate, they would update it in the system. So when it came to producing a deformation grid, they said, we don't need one. We've already kept this up to date. Whereas most of the other jurisdictions, states and territories, needed some sort of deformation to model the changes that were occurring. And here's what it looks like. The image on the left-hand side is showing you what that 7 parameters will do. That's the conformal component in green. That's all moving in the same direction. Then if you look at into the middle, you can see what's left over. Where's that distortion? Where's that residual? And then, as Richard was just talking about, then you can develop a grid, and you see the grid dots there. For each dot on that grid, you can do some sort of interpolation to try and determine what that residual is going to be at those points. And then that gets recorded in the deformation grid. So then you can apply that 7-parameter transformation and then apply the deformation to try and move you closer to where the updated coordinate set should be. This is what it looks like from a 3-dimensional perspective that's been done within New Zealand. So they're using deformation models to estimate the deformation of the Earth's crust, including tectonic movements from things like earthquakes. So New Zealand have the New Zealand Geodetic Datum 2000, and it's defined through its relationship with ITRF via a deformation model. And they've got an interesting case. They've got 2. They've got a reverse patch and a forward patch. And the reverse patch, it allows people to correct coordinates in the past to account for deformation that has occurred since a specific reference epoch, while the forward patch projects coordinates into the future or corrects them to the present to reflect the ongoing deformation. And the reason they've done both is because they recognize that they have two different user groups. So they develop patches that allow the user to choose, do I need to apply the reverse patch or the forward patch depending on their application? This is something I really like about, we tried to copy in Australia a lot of the things that New Zealand did, because I always find that they were doing things that were very practical. They're always thinking about it from a user perspective. And I think that's critical in the work that we do, because our job is to make the lives of our users a lot easier. To help with that, there's some software as well. So to our good friends over here at Geoscience Australia, they would know all about Geodesy. It's a wonderful Python library that Lisa's team and Jack have played a key role in helping to develop this kind of software that sits in that GitHub repository that allows you to do some of this, these geodetic conversions and transformations. So I would encourage you to have a look there if you're looking to try and develop some software or use some software. It's a great resource that you can access. A lot of this information is also described, as I said, I like the details. I like to be able to define how things were done, what assumptions were made. And so all of this is also reported in the Australian Geospatial Reference System Compendium. And as you're developing your roadmap document, you'll see there's references across to this compendium a few times. And this is guidance for you. I don't want you to look at it and feel intimidated, because it's a very big document. It's including about 15 years worth of work that was done to summarize. So don't feel like you've got to do this all on your own within a week, but there might be pieces of information in there that are valuable to help you understand how to explain this or how something was developed. I hope you find it as a good resource for that. A couple of other things to think about is services, transformation services. So once you develop these transformation parameters or grids, how do you want people to use this? So the one on the left-hand side here is a place where you could drop your files. You could drop in like Excel spreadsheets, shape files, JPEGs, GeoJSON, GeoTIFF, whatever it might be. You could drop them in there, and then there would be some software in the background that would do the transformation of that data for somebody. So this was really important for implementation of the new datum in Australia, because it was an easy place for someone to go and drop in their data set and then get the information back. They didn't have to worry about all the complexities of, or trying to make sure that they were doing the transformation the right way. A similar tool is shown on the right-hand side that's done by the Royal Observatory of Belgium on behalf of the UREF network. They have a lot of other software and tools that you can use as well. So you might find it interesting to have a look around there if you're looking for ideas on how you can communicate and help stakeholders in your country. And then there's this challenge. This is really where standards come into practice. And I mentioned before that it's really your job to abstract the user from the complexities of standards. And this is why. As you can see, it's complex. To go from GDA 94 to GDA 2020, there's a range of different ways to do it. You could use the 7 parameters, as I mentioned. You could also use the deformation grids, as I mentioned. So that means you need to provide that information described in EPSG and ISO standards so that the user knows, how do I transform from there to there, and which one do I use at which time? You've got to describe this to people in the standards, otherwise they're not going to know which one to use. The key bit there is you have accuracy statements to tell them, how good is this model compared to that model? What sort of data set would I be using to transform from this datum to that datum? And then from GDA 2020, how do I get to ITRF 2014? Well, you can do a plate motion model, as I mentioned, and it just rotates through time and moves the Australian plate, and that's accurate at the millimeter level. Whereas if you come across to going from GDA 2020 to WGS84, in the case of the generic version of WGS84, that's only accurate to 3 meters. And I was very keen to make sure that was reported, because I was trying to discourage people in Australia from using WGS84 for high precision applications. because WGS84 is classified as a low accuracy ensemble datum. And an ensemble datum means it's actually encompassing the now 8 versions of WGS84 that have been available over the years. And there's no official transformation parameters to move between them. So if you want to use something that is accurate and reliable and precise, it's ITRF should be the reference frame you're trying to use for your country.
Totally agree that WGS84 is from a geodetic point of view, is a bit of a disaster for anything precise because it's not a legally traceable datum. You have to be in the US military to access that, so that's an issue. Another point is the distinction between distortion and deformation. We had a lot of discussions with Roger Lott about that and colleagues in the UK because they have a distortion grid to go from the OSGB to ITRF or URF. The distortion is basically not deformation. It's only deformation if it's not actually modeled. So the distortion is actually like a different thing from deformation. So we had a lot of discussion about that, and distortion really is inaccuracies that are embedded. So it's basically truth minus observed is your distortion. So obviously there's inherent error in older datums. And if you remeasure those and there's been no deformation, you'll see a difference. And that's the distortion. And the deformation is actually like a geophysical input into it. So the other thing that was very, we discussed a lot was having the grids having associated uncertainty with each node. So if there's a displacement or a velocity at each node in the grid, it really needed to have an uncertainty metric in there so that it could be useful. And we thought about, should we put all the covariance terms in there? And you can do that, but it makes it quite unwieldy. So the basics were the uncertainties of each of the displacements or velocities was the critical thing to put in there. Yep.
So that is able to be recorded in the grids. There is an uncertainty value.
Yes, so NTV2 actually has that capacity as well, and GGXF maintains that. So you can actually have GGXF is scalable, so you can have anything you like in it pretty much, as long as it's as long as the metadata in the header of the file can be traced back. You can utilize that information however you like.
That's good. Thanks. Have you looked into that at all for grid stuff? I know with geoids it can be quite big. Have you looked into other alternatives for that, Jack? Okay. Good to know. Come on, there's got to be other comments or questions. We were talking a lot about it before. Yes, thank you.
So, okay, we have like transformation parameters from one ITRF to another ITRF, right? So let's say I will give you an example of India. So in ITRF 2020, 4 IGS stations of India are used, right? But for computing the transformation parameters, none of the station from India has been used. From ITRF 2020 to 2014. Yeah, so if you really see the ITRF website, right, that's the case. Now, I'm not sure about the APREF transformation parameters, how many stations are used. So if I'm using, let's say, some of the APSG codes, right, for the transformation parameter. So how reliable would they be? Right? Will they be like applicable to my country or not? My stations? So that's the question.
It's a great question. I'm very surprised that none of the stations were used in the development of the model. Do you know why? I wouldn't know why, Richard.
Yeah, we had a big discussion with Zuhair, who develops the IRS. Zuhair and Paul Rebichon, and the whole team in IRS that do it. They exclude a lot of stations around the global network particularly if they're not bedrock sites or very, very stable sites. So a lot of global ITRF sites are in urban settings. So they're in a sedimentary basin. And there's actually a lot of, if you take the plate motion model away for that area, you have this residual velocity, and that's due to the fact that it's actually in an unstable setting. So a lot of the stations have been stripped away if they're outside that sort of 2 sigma test for the transformation, and that's just unfortunate. I guess in India, your core sites are in urban settings, and there's a lot of sedimentary uplift or subsidence because of it.
Maybe, but when I saw the velocity model that is also published on ITR website, so I think it somewhat gives a nearby true estimate of 5 centimeters per year. So still, and I think IISC is one of the IGS sites from India that has been used since ITRF 2000 realization every year since. So if there would have been some kind of problem like this, right, it might have been communicated so that it can be solved, and some of the Indian stations could have been involved in, let's say, transformation parameters. Because for velocity, there's always some kind of a station. We do see the velocity models. So how it can be reliable? So I'm not sure.
Yeah, I think it's a great question, and thanks for sharing your discussion that you had with Zahir and Paul. I find that very interesting. They talk about geodesy as a science. There's very much still an art form as well. And it's the same with a lot of types of science. So I knew they would have a reason, but I don't doubt that the transformation parameters would still work very well within India, just even without using a site from the country, because it's moving of the plate. So they would have modeled that very well and taken into account the geographic distribution that they need. But I think coming back to the point I made in the previous slide deck, it does show the value of being able to develop your own as well, your own plate motion model, own transformation parameters, because you'll ultimately get a higher resolution feel for that deformation across your country. So particularly someone with your skill set, I think you'd be able to work with the Survey of India to try and develop that and explore that. It'd be an interesting project to then compare with what you get from the standard model out of ITRF and how much better resolution you get out of your localized work. Yeah, that's a great question though. Thanks for asking. Yes, thank you.
I want to share about the transformation epoch in Indonesia. So we are using a semi-dynamic datum called SRJ 2013, but it is called semi-dynamic because it is not fully dynamic like maybe like in the Australia. We share about the transformation epoch. We set the initial epoch at the regularly periodically first in the 2013. And then, first in the epoch of 2012.0, and then we update to the 2021.0, and then we doesn't like the slide you mentioned about the reverse patch and forward patch. So we trying to set to the exact epoch in the 2021. So all of the current measurement, just we trying to ignore on the 2021 until the current epoch, just to ignore, because it's very difficult to for non-specialist user to implement of the this change of the current epoch. Thank you.
And what do you think? Can you estimate what the difference is between the current epoch and the 2021 epoch? Do you know roughly what difference that is in centimeters?
It's different between a region in western part of Indonesia is maybe 2 until 3 centimeters, and then the challenges in the eastern part. Sulawesi, and then until to the Papua, and the Papua New Guinea is the different direction. Like the western part is going to the east, and then the western to the eastern is going to the north. That is different direction of the Euler. So that's the challenges of our definition of our deformation model, because right now, currently we set our deformation model is based on the linear model. So we just ignore about the displacement of the plate, especially in the boundary of the plate. We just ignore that. Okay.
Thanks for explaining. That's very, very good. It's clear to me. And it's fit for purpose, right? That's what I keep saying. It may not be the most accurate solution of the day, but it's fit for purpose. If your users are happy and it's not stopping them doing the work that they need to do, it's a good solution. Yeah.